Okay.
On number 2 and 5, there were the answer, like the answer for X,
Right.
The brackets.
Right. Okay. I think I explained this when I did. When I only put one blank in there, it's so tiny, it was hard to do. So that's one number here, one number there. Okay. It's just that they don't connect with dots, dashes. When they're bigger, like here, well, I did 2 dashes on those too. But this was big enough that you could see it well, and they spaced them out. And it was just, I was trying to. The last time I had done it, it was just too narrow, and people were having trouble writing. I was having trouble reading what it's a number there and a number there. And yeah, and same thing down there. I thought I said that when I passed it out, but maybe I didn't. I don't remember. Okay. Now, I did want to make one other announcement, or at least one, before we get going. As far as I know, for once, I think office hours are about normal this week. I don't know of any changes there, but I did want to remind you, you probably have seen it in emails, the student course evaluations are open, so please do those sometime between now and the end of the term. If you wanted to wait till later, you can, but just don't forget to do them. I feel like I get feedback every day in class, but I still like to see what students say when they're anonymous, okay? And by the way, there's no way I'll ever know who says what, because they won't open anything to me until there's enough people who have done, and then it's all a composite. So there's no way I'll know anything about who is marked what. So don't ever fear something like that. But I don't know of anyone who would really bother to try to find that out anyway, but some might, but I certainly wouldn't. But there's no way you can do it, because they wait until there's a certain number of entries there before they do. What they do let us know is who has responded and who has not. That's all we know, and then we get a composite once enough people have responded. So please get those done. Now, I started all that by, I do get some feedback from you every day, I feel like, but I still like to hear what you say when, behind closed doors, so to speak. But the other things, you've done student course evaluations here before, right? There's usually 1 or 2 others that you're asked to do, like registration or library or food service. I don't know what all they are, grounds, whatever. Those are there. Now, sometimes that's the best and sometimes almost only feedback those folks get. So please do those as well. I really value the student course evaluation. You talked about the course and the instructor, but the other folks really need to know the other things as well. So please get those in. I don't see those. I don't even care to see them, but those people really do. That sometimes they don't have any feedback short of that. I doubt if there are any staples in it, but you can try it. I think that one got jammed a while back, and does it have it? Look at that. Someone must have fixed it. Thank you. Okay, and we'll get that done. Let me, while I'm sitting here, go and get them.
One more question. Nigel told me that Monday that we weren't here, you were talking about number 7, I believe, that you would add another bracket. Yeah, this one? 9.
No.
That we could add another bracket to it?
If you needed to, yeah.
Okay. Because I worked it out one way and I had 4 brackets,
right.
And then I worked it out another way and I got 3.
Okay, right. I try to go back and redo if another answer comes, because some of these do have more than one approach. But on a few of them, if it's not an elementary matrix, then it sort of messes up everything. So, and a couple of them I've seen that have had 4 brackets on them. One of those was an elementary matrix, so it sort of messed up the whole picture. But yeah, it could easily happen. You could have more than, and they can be in different order, you know, because the order doesn't matter that much either. But yeah, you can use more if because there's the most efficient way and less efficient ways to do any problem just about. So yeah, that could happen. All right, any other questions before we get going today? Okay, we're on page 130, chapter 3, determinants, 3.4 applications of determinants. And where we are on page 130 is the beginning of Cramer's rule. Okay, and unfortunately I got started on this last time, but we didn't have time to get the whole thing done. If you remember, when you're solving systems of linear equations, 2x2 systems back in some earlier algebra course, probably high school or somewhere else, you use a process called elimination by addition, maybe different terminology for it. That's what they were doing here, was eliminating one variable and then coming up with the other one. And we got that far. If you watch the YouTube video on it, you saw us get that far. And ultimately where we wound up then was, let me get my pen. Boy, the system is so slow today. Okay. We got down to this point. Okay. You see on the top of the page there that says x1 equal, and then it's b1 a22 minus b2 a12 blah blah blah, and x2 then is equal to what they note there. I'm going to write that we got that far last time. X okay 1 is equal to b1 a22 minus b2 a12 over a11 and here's Nigel. Okay, good to see you. Okay, a11 a22 minus a21 a12. Doesn't matter what order, I'm just trying to write it the same way they do. And then the x2 is equal to b1 a11 minus b2 a21. Yeah. Okay. Divided by a11 a22 minus a21 a12. Now, yeah, I want you to take a look at those and see if you get any pattern. You see anything in common? Yeah, same denominator for both. Okay, and in fact, in the thing you just turned in, I think you solved the 2x2, and you probably came up with the same denominator in both of those, or a multiple of the denominator that reduced to it. So it's not too surprising you got the same denominator. Okay? Page 130, chapter 3, section 3.4, Cramer's rule. Okay. Now, how about that denominator? Okay? Since we're writing this as elements of a matrix, right? Let's write that matrix down. If we had been before, we've already had it. But what would be this equation, you might say, as a matrix equation? What would be your coefficient matrix? Typically, A11, A12, A21, A22, multiplied by X1, X2 equal B1, B2. Okay. Yeah. All right. Now, with that in mind, what does that common denominator look like? What is it? Especially when you consider the title of the chapter. Oh, it is a lot like the determinant. It is the determinant of your coefficient matrix. A11, A22 minus A21, A12. It doesn't matter which order you do it. I'm trying to do it the same way. So basically, what we have here is our X1 and X2 have as their denominators the determinant of the coefficient matrix. The book writes it out. I'm a lot too lazy for that. So let me just put, if it's okay, have this be A and this be vector B. Y'all okay with that? And then we'll put this denominator to be the determinant of A. You okay with that? All right. Now, I probably shouldn't do that, but I'm going to because I'm just that lazy. All right. Now, let's take a look at that numerator. What does that, how is that sort of related maybe a little bit to the denominator, to that determinant of the coefficient matrix? Do you see any patterns there? Any similarities? Let's take X1. They both have A22 right there, don't they? Okay, so that's there. And then over there they have an A12, so that's there. But they don't have these. What do they have in place of this? This. You're absolutely right. So that would be, this time I'm probably going to have to write it out, B1, B2, the determinant of that, A12, A22, right? How about X2 though? What do we have there? Say again? The first column. Yeah, okay. It has the A11, A21, and instead of the second column, it has the B1, B2. And its determinant. Okay? And these, by the way, were the coefficients for the X1, and these right here, were the coefficients for X2. So what they've done is, and basically this gives us our answer without any elimination. I mean, we did elimination by addition, and we did all the other parts here. And here's Jonathan. I'll wait just a few more minutes, hoping that Marcus will come in, and I'll make the announcements I did earlier. One announcement, fairly important one, but I'll catch up those when hopefully Marcus comes in, and so everybody will get to hear it. So sure enough, here we have the solution to your system of linear equations using only determinants, okay? And that basically is what, one other thing. What does this also tell you about the determinant of A? Can't be 0, okay? And if the determinant can't be 0, what does that mean about the matrix? It's what invertible matrix. It's a non-singular matrix. It's all those things we've been talking about before, and of course that has to be true. If that determinant is 0, then that was a dependent system. It has an infinite number of solutions, or it has no solutions. but it doesn't have a unique solution. So all this stuff basically is tying together pretty reasonably. Okay? So that determinant form of a solution is called Cramer's rule. So let's clear this, unless you got questions about it. Okay. What's that? Okay. We had done the earlier part last time. You'll have to go back and watch YouTube and pick up how we got to stage 1 here. But we did it. Then we picked up here and went to that.
Did you pass out the test Wednesday?
Did I?
You said you were going to pass out.
Yeah. I'm trying to remember. Did I? Do you remember? Were you here Wednesday? I didn't pass it out. I didn't remember passing it out. I had planned to, but I think what happened is I didn't have it run off yet. So let me... Let me make sure. Okay. I do have it made out, but I don't have it run off, I think. Let me just make sure. I don't have copies here somewhere. Actually, I do have one. I have two. Why do I have two of these if I didn't pass them out? Nigel, you were here Wednesday, and I didn't pass these out. Well, I do have two, and I can give two of you to you now. I'll have to make the other two copies right after class. And here's Marcus. Perfect, it's in the ding, 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 ding. All right. Good to see. So before, I was going to pass them out today because we just didn't get as far as I intended before. So remind me again right at the end of class. I'll go down and make 2 more copies. But
Okay.
You got it. Okay, since I got everybody here, let me say the announcement again. They have open student course evaluations. If y'all have read your emails, you've probably already seen it. Any of you already done the student course evaluations yet? Okay, you don't have to have done them yet, but do them before the end of the term. And if you want to wait until you actually see that final exam, you can wait till then. But if not, I mean, be sure to please get those done. And as I was telling Manuel earlier, I'm also a department chair, so this is how one of the methods by which I evaluate my instructors, because I have to do annual evaluations of them. I have to look at these, so I really want everybody to do these for that reason too. But also the other departments like food services or registrar and all these others, this sometimes is the best and maybe the only feedback they get. So please do the other evaluations they ask you to do. All right, so let's use Cramer's rule then. Okay, let me clear what we've got, and we will use Cramer's rule to solve a system of linear equations. Here's the system. 4x1 minus 2x2 is equal to 10, and 3x1 minus 5x2 this is example 3, is equal to 11. And I really do not like that system of equations. Anyone want to hazard a guess why I might not particularly like that? Yeah, the first equation that you could simplify right off the top. But we won't. We'll do it just like they expect us to do it. What would be your step if it said, use Cramer's rule to solve that system of linear equations? Now, number one, you'd probably say, look, I can just solve that by elimination by addition. You can, and it's pretty simple. But let's use Cramer's rule. You might also say, look, I can just augment the matrix and, and do row reduction. Pretty easy to do. And it is. Kramer's rule is no easier, in fact, maybe a little more involved, but let's use Kramer's rule since they told us to. What would be the first thing you would do in Kramer's rule? Say again?
Separate them out.
Okay, and what do you mean by that? Say again? Yeah, find the determinants of what? 4. You said 3 down here. -2, -5. Notice how strangely he's doing. Okay, no, it's no problem. Okay, what's the determinant of that? And that's really an easy one to do. What is it? You said -14? Yeah, -14. Okay, agreed. Everybody got it? Okay, that was pretty easy. Next part. You know, I'm really regretting I didn't do it. I wish we had reduced that first equation. There's no reason to have the big numbers when you don't need them, but we didn't, so we'll go on. What's next? Okay. Give me some numbers.
10.
Okay, 10. Second. Okay, beneath it, 11. -2, -5. Right? And what's that determinant? Okay, -50 plus 22. -28, is that what I heard? Yeah, -28. Okay. One other? Okay, 4, 3. 10, 11. Okay, what's that determinant? I hope it's more like 14. Okay, good. Okay, 14. Okay. Okay, we did 3 pretty easy determinants. That wasn't too bad. So far, this is pretty easy. Can you give me an answer yet? You got over -14. Yeah. So x1 would be -28 over -14, which would be 2. And x2 would be, second, 14 over -14, which would be -1. Hey, that wasn't too bad, was it? In fact, that may be the easiest way to do this on a 2x2. Now, can you imagine the 7x7? No, I don't even want to go there, but that'll be on the test, but never mind. Let's just kidding. Okay, let's see who was awake. Okay, let's check and make sure our answer is right, though. If you plug in a 2 here, 4 times 2 is 8. Say again? Plus 2 is 10. That's fine. How about this one? 6. Plus 5, 11. Yeah, there's our solution. Came out right, and that's as fast as Gauss elimination, isn't it? I mean, just about. Maybe not. Maybe a little more writing, maybe, but it's not bad at all. Yes. What? Okay. Okay. Here's what we did. Okay. Notice this was our coefficient matrix from here. That's our denominator in both cases. Okay? Now, the numerator in both cases, in the first case, since you're looking for x1, okay, you, instead of writing the coefficients for x1, you write the constants, 10, 11, and leave the other two coefficients in your coefficient matrix the same, and do that determinant. That makes your numerator and the coefficient matrix made your denominator. The determinant, that's that. For the x2, you substitute the 10, 11 in for the coefficients for x2. So they go here, leaving the x1 coefficients just like they were, and then that's the numerator, that's the denominator. Okay? Always the determinant of your coefficient matrix is your denominator for all your variables. Okay? And your determinant for the numerator with the constant plugged in for the coefficients of the variables you're looking for, the component you're looking for. You put the constant in there, and you put the constant in here for x2, and that gives it to you. That's Kramer's rule. Pretty nifty, huh? Okay, and by the way, Kramer, well, let me back off a moment here. This was the other thing I was going to say. This class, ding, 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 is my only class so far this term to have 100% of your research papers in. I was just going to say you can write on Kramer. You don't need to. All of you have turned in research papers. Very good. Thanks for doing that, getting them done early. Now, still missing one test 1, so I need that in. And I think I'm still missing one test 2 as well, so I need that in because today you're getting test 3. So please get those in, because I'd love to get these tests back to you, but I can't get them back to you. I can't return your research papers, but I can return your tests as soon as I get them all in. So please get those in. All right, let's see how the book did it. Look at that. They got x1 equal 2, x2 equal -1. Good for them. All right. Kramer's rule generalizes easily to systems of n-linear equations with n variables, but of course finding determinants for bigger and bigger matrices get more and more complicated, but they're doable, okay? And what's more, they're programmable. So you can program a calculator, a computer, some calculators even, to do these for you, okay? So let's do that generalization to 3 by 3, which they do at the top, which is a lot of writing. I'm not sure it's a lot more instruction, but just so you'll get the concept, a11x1 plus a12x2 plus a13x3 is equal to b1. Okay? a21x1 plus a22x2 plus a23x3 is equal to b2. And a31x1 plus a32x2 plus a33x3 is equal to b3. There is a good generic 3 by 3 system of linear equations, 3 variables, 3 equations. Okay? Now, they just happen to pick x3. Can you tell me what x3 is in terms of determinants? You want to go for numerator or denominator first? Numerator first. Tell me what the numerator is. A11. Okay, you're going down. Okay. A21. You're going down. Okay. Now you're going down. Okay. A31. A12. A22, A32, B1, B2, B3. That determinant, if I could connect the dots, how about your denominator determinant? A11. Okay, you're going across now, right? Okay, confusing me. Okay, A12, you're trying anyway, okay? Second, A13. Unless you're going some other direction. Okay, all right, next. A21, A22, A23, A31, A32, A33. Yep. Now, of course, those are more involved determinants than 2 by 2s, which are pretty easy to do. But the procedure's the same. You take your coefficient matrix here, that's always your denominator. Your numerator is always that coefficient matrix, except for the variable or the component you're looking for, replace those coefficients with your constant. And then, it's just a matter of doing your determinants. And if you have something that programs and does determinants for you, plug them in, get those determinants. You got the X3 done for you. All right, now that leads to Cramer's rule, and here's what, this is theorem 311 in your book, page 131. If a system of n linear equations, okay, n variables, what does that tell you? Got n linear equations in n variables, what do you have? A square matrix, a coefficient matrix that is square, okay? They call that A, okay? And the A is going to be an n by n matrix, a square matrix. And that's the only one you can deal with determinants. You have to have square matrices. Okay, now here's a caveat here. That coefficient matrix A has to have a non-zero determinant. If the determinant of that matrix A is 0, hang it up. There's no solution. Don't even go any further. So this gives you a real quick and dirty way to see if you got a solution. Then the solution. But if you have a non-zero determinant, okay, A, then your x1, your first component of your the first variable component, first variable, I guess you would say, would be determinant. I don't like writing this. I'm just going to do it this way. A1 over determinant of A. X2 is equal to the determinant of A2 divided by determinant of A. And A3, or X3, is the determinant of A3 divided by determinant of A. Now, number one, all three variables have the same denominator, okay? Now later they may cancel some things out and they may not look like the same denominator, but it can be written that way. So that's number one, and that's that determinant of A. Do it once, you've done it. You don't have to do it every time, whatever the determinant of A, that's going to be your denominator, okay? Now, let me clean this up because that really does look bad. Okay. That's a little neater, but not much, but a little bit. Now, what's your A1 and A2 and A3? That is your coefficient matrix, except that in place of the coefficients for x1, you put the b's. And instead of the coefficients for x2, you put the b's. And instead of the coefficients for x3, you put the b's. And that gives you the A2, A1, A2, and A3. Okay? And by the way, I just did 3 of them. If you have this as an n, it would go dot, dot, dot up to the determinant of A sub n over the determinant of A. and that would be your x sub n. Okay? Where the ith column of A is, let's see, of A sub I, where the I is 1, 2, 3, up to n, where the ith column of A is the column of your constants. In the system of equation. In other words, your B's. Okay. That's what your ith column becomes, and that's what the A sub I is. It's the one with that substitution done. Okay, they have a little proof here, and it's a nice little proof, very short. I think it's something you can do. I won't take class time to do it because we probably need to move on so we can finish this today so we can get moving on the next thing. Any questions before we do example 4? Okay. If not, let's do example 4. Here's our system of equations. 3 by 3, old joy. Okay, minus x plus 2y minus 3z is equal to 1. Okay, 2x plus z is equal to 0. 3x minus 4y plus 4z is equal to 2. Okay? It says, don't use any other technique, use Cramer's rule to solve that system of linear equations for x. They don't ask for y or z, just for x. So let's just do x. Where would you begin? Okay, of what? The coefficient matrix, you said? Okay, so the determinant of that coefficient, what is that coefficient matrix? You tell me. Negative 1, 2, negative 3, 2, 0. Is that a, yeah, that's a 1. I was thinking that was a 7, but that's my z there, okay. 3, negative 4, 4. Okay. Now, how do you find the determinant of a 3 by 3 like that? There's a couple of ways. You tell me what you would choose. Second? Boo hiss, okay. All right. Without the book, how would you do it?
Use the second row.
I would do the second row. I would definitely do either second column or second row because that has a 0 in it. Okay, so let's use the second row. I like that one. And we're going to expand that second row, and the determinant of that will be, let's start with the 2. Okay, so that means we're going to eliminate the first column as well. But what about that 2? What's one of the first things we note about it? It's in a negative spot. Its position is a negative position, so that becomes a minus 2. Now, do you know what we mean by that? Your positions are always start with plus, and wherever you go, as long as you go right or left, up or down, plus, minus, plus, minus, plus, minus, plus, minus, plus, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus. I mean, however you go, you're going to always get the same. So that is in a negative position. Plus, minus, okay? So you do a minus 2 there times the determinant that's left over, which is, okay, what did you say it was? Okay, oh, you wrote it out. I was just going to do it. What is that? A little louder. Ooh. 8 minus a positive 12. Minus times minus plus. Okay. Say again? Okay. All right. Okay. If you'll get the numbers, let him get this. No, I'm just kidding. Okay. What is it? Negative 4. Okay. Whew, I think. Okay. Next. And this is why we chose the row with the 0 in it. Okay. We're going to keep that second row. We'll remove these construction lines there. But now we'll go to the third entry, because you see the 0 entry would give us a 0. Yay, I wanted to eliminate that, so we did. So now we use this one, and first question is, what's the sign of that position? Negative, because plus, minus. Yes, you're right. Or plus, minus. However you get there, it's going to be a minus. So it's going to be a -1 times, and then do the determinant of what's left. -2 on the first one. Okay. Yeah, because that's a +4 minus 6 is -2. So what's the determinant of that matrix? 10. And number one thing that you notice about that is what? It's not 0. Good. This does have a solution. If that were 0, hang it up. There is no solution. But it's a non-zero number, 10. So that's going to be, by the way, your denominator. Now, all they're asking for is the x value. Okay? So, x is equal to, where can we put the 10? In the denominator. There's your denominator. Now, what do we do to get the numerator? One. You're going down now? Okay. 2. -4. -3. 1. 4. Oh, wasn't Emmanuel clever here? Not only did he choose the right column because it had a 0, right row because it had a 0 in it, he also, of course he did, notice that there was a 0 there, didn't you? No! Okay. But that works out real nicely because that replaces your x coefficients. And now you got a really simple one to do. What is the determinant of that one? Which would you like to use to determine that? You can choose any one. Second row again, okay? You didn't have to use the same row, but by doing that substitution, boy, it comes out for us. Good. Next. Third column, okay? And what's the first thing you note there? And what about it? Negative position, so that's going to be a -1, and then guess what? That's exactly the same one. No, it isn't. I wanted to say it, but it wasn't. What does that give you? -4. Okay. Is that all of it or the first part of it? Okay. Continue. That part's -4. -4 is -8. And that gives us 8. So your x is 8 over 10. Yes. Oh, okay. Okay, you want the test now? You have to take it also? All right, good deal. Any of the others? Okay. Let me give one. Let me run down real quickly and make the other 2 copies. I wish I had this done. Oh, and one other thing, one little correction here. This says test 2, it is test 3. because, oh, what I'm going to do is pause my screen. All right. So what was our x? It's what? 8 over 10, which is 4 over 5, or 0.8. I mean, you could write it many, many ways. Okay. That is our, they did 4/5. It doesn't matter. Now, it says try applying Cramer's rule to solve for y and z, and let's see what we get there too. That's pretty easy. How do we get y? What do we do? -1, 2, 3, going down. 1, 0, 2, going down. -3, 1, 4, going down. And which you want to use there? It's a toss-up here. You don't have to use the same one, but what do you want? Say again? Same one? Okay. Second row. Okay. Second column is just as easy, but we'll do that one. And what does this give us? -2 times 10. Okay. Okay. Let me just clear out a little bit so it'll be easier to see. -1. -5. And what does that give you? Which is? Okay, so what's your y? -15 over 10, which is -3 over 2. Very good. Now I don't have a lot of room, but what do we need to get to z? You can already give me half of z right now. What would it be? Denominator of 10. Okay, so let's figure out what that numerator is. I guess I'll erase. I was going to just write it in the blank, but we'll just erase here. We've already done that a while back, so what do I put for my z? -1, 2, 3 going down. Why didn't I leave some of those numbers in there? Next. 2, 0, -4 going down, and 1, 0, what? 1, 0, 2. Okay, good. All right. Now what will we use? Second row. Good choice. And what will you start with? -2. Negative because it's a negative position, and 2 because it's a 2. Okay, and what goes next? -8. All right, and that'll be -16. So what's your z? Which is? All right, let's see how the book did. -3/2 and -8/5. Good for them. Okay. Do you see how that works? So Cramer's rule is one pretty nifty way, not necessarily all that much easier, but just another way to solve systems of linear equations using almost strictly determinants. Okay. Now, the section is applications of the determinants, Cramer's rule being one of those. Let's do another, and that would be, this is pretty interesting. Area, volume, and equations of lines and planes. Okay? Determinants have many applications in analytic geometry. One application is finding the area of a triangle in the XYZ plane, which, if you think about it, is a pretty abstract type of thing to do, isn't it? If you have an XYZ plane, I'm going to be in the first octant, I call it that, positive X, positive Y, positive Z. What if I have a point here, and a point over here? Can you give me the area of that triangle defined by those 3 points? Ooh, messy, okay. What's the base? What's the height? I mean, how do you calculate those? It's, I guess, doable, but I sure don't particularly want to do it, okay? Well, here's how you do it. The area of a triangle with these 3 vertices, this is in a plane, sorry. It works there too. X1, Y1, X2, Y2, and X3, Y3. Okay? This is in a plane. 3 points in a plane, but they're not collinear. They're not, they're just 3 random points in the plane. How do you find the area of that triangle? Here's the formula for it. Area is, this seems strange at first, plus or minus. Now, why does that seem strange? Or maybe it doesn't seem strange to you. But to me it does a little bit, because areas are always positive. Now, draw me a negative area. I want to see it, No, can't do it. And then a strange coefficient of 1/2. Okay? But then we do the determinant of, now here's the interesting thing, x1, y1, 1, x2, y2, 1, x3, y3, 1. A 3 by 3 determinant, it has to be a 3 by 3 thing. You have your 3 coefficients, your 3 coordinates, okay? x1, y1, x2, y2, and x3, y3. Those are your 3 rows with a 1 as the third entry there, okay? And then you do that. Now, the question of why you have the plus or minus here, because a determinant can easily be plus or negative. Area is always positive, so you use the sign to make the area positive. So that's why the plus or minus is there. The 1/2 is not really so clear yet, except remember, what's the area of a triangle anyway? 1/2 the base times the height. So it might have something to do with the parallelogram that triangle is associated with. It's half of that, but we're not going there, so we'll leave that alone. You use either the plus or the minus sign to make sure you get a positive area. Otherwise, you can't do it. Okay, and I really like this little proof here. It is a geometric proof. I like geometry, and you can follow that through, and sure enough, it has to do with a trapezoid. What did I say? A parallelogram, but it's actually a trapezoid. You take the area. Yeah, I like it so much, I'm going to do it. Okay. Okay. Here's x1. Okay. And that point down here is going to be x1, 0. And here's your x1, y1. So that makes this be y1. Okay, not that we need that, but just do it. Here's, it doesn't really matter which one they do. They put the x3, y3 up here. x3, 0 here. And this will be y3 here. Those are sort of immaterial, so this would be x3, y3. And then somewhere down or over here, they put x2, 0. And this will be y2 here, not that it matters any, x2, y2. And then if you close in this triangle, okay, you want the area of that triangle. okay? Now, how they say do it, look at this trapezoid, okay? All right? And its area is 1/2 the base times the sum of the two heights, okay? We're not going to do it, but that's how you go about doing it. You look at the second trapezoid here, this one here, and you do its 1/2 the base times the 1/2 the base times the sum of the two heights. Okay, that's the area of a trapezoid. Okay, add those two together, but then subtract off this trapezoid that goes from x1, y1 to x2, y2. Subtract this one off, and then you get that one. And if you do that and carry it through, you'll see you do get this determinant. Not really clear that you would have, but indeed you do. Okay? Now, if the vertices do not occur in the order x1 less than x3 less than x2, or if the vertex x3, y3 is not above the line segment connecting the other two, then the format may yield the negative of the area, so you use the plus or minus to correct that. So, I'm not going into gory detail, but that was the fundamentals of how you do that. So let's do example 5, which actually is pursuing that. Find the area of a triangle whose vertices are 1, 0, 2, 2, and 4, 3. Okay. Without having to draw a picture or anything else, you tell me what the area is. Plus or minus 1/2 times the determinant of one what? 1, 0, 1? Is that what you said? Okay, next. 2, 2, 1. 4, 3, 1. Okay? Now, how do you propose to find that determinant? You got several possibilities you choose. I like the first row. Okay? So we're going to use the first row to do it. Okay? And where we begin there is the first column as well. So that's going to be, I'm going to write down your plus or minus 1/2, okay? But let's go with the determinant. Okay, now that's not a matrix notation, it's just a square bracket. What's the first thing you ask yourself about the 1? What sign is that? It's a positive position, so that's just going to be 1. And then you do the determinant of what's left, and what's that? A minus 1. Okay? And then, once you've done that first entry, we'll delete that one and these marks and go to the third. Okay? And what's the first thing you ask about that one? Its sign, and what is it? Positive as well, so that's going to be a plus 1 times what determinant do you have there? 6 minus 8 is negative 2. Okay? So this is going to be plus or minus 1/2 times.
So when you take out the 1 and you block out those two columns, it just leaves 4 and 2.
Okay.
It just leaves 2, 2, and 4 and 3.
Okay, you're talking about just this last part, not the first part. Okay. We had already done this one. Right. We blocked out that row. And the row we chose, okay, we leave it blocked out. Block out this column. use this element here, which is a 1, but it's in a plus position, so it's a plus 1. And then you do the determinant of what's left there. And then you go to this one, because this is a 0. If you did that one, it'd be a minus 0, but 0 times anything is 0, so it wouldn't contribute anything. We go straight to that one and block that one. We already had that row, block the column, and that's also in a plus position, so another plus 1 times the determinant here. 6 minus 8 is negative 2.
So you use the whenever you pull out this like line, it's the line like the wait,
Say that again.
when you block it off, like I guess.
Yeah, you use this element, you use this one first and this one next, with its position sign. If this had been a minus here, it's a plus position, so that would have been a minus 1. But it's a plus, so it stayed a plus 1. And that also is a plus position, so that stayed a plus 1. And then you do times the determinant of plus left. Yeah.
Okay, I get it.
Got it. Okay? So what do we have from that point? Negative 1 minus 2, and that would be plus or minus 1/2 times negative 3, and that would be 3/2. Done. You always use whichever sign gives you the positive answer. The area would be 3/2. I've got to find, there it is, okay. 3/2 square units, 1.5 square units. Now, when we were explaining this or doing it, did any of you come up with, well, what would happen if? Did anyone think of anything like that? Trying to throw wrenches into the problem? Oh, you should have. What would happen if those 3 points were collinear? What's going to be the area of that triangle then? 0. So that means your determinant from those 3 points would have turned out being 0. So plus or minus 1/2 isn't going to help you any there. So yeah, if you turn out they're collinear, but guess what? You know, those would be dependent equations, which would give you a determinant of 0. So sure enough, that would be the case. All right. So that's their next supposition. Suppose those 3 points in example 5 had been on the same line. And I didn't draw the ones, but to make those happen, you'd have to reverse the coordinates of the first point. Make it a 0, 1 rather than a 1, 0. And in that case, let's see if we can, I don't know if this will be beneficial to do this way or not, but we'll just swap those two, and that stays the same, and those stay the same. I don't know. All right, let's see what happens. This time we're going to have 0, 1 rather than 1, 0. Is it time? How could it be? Just when we're beginning to have fun. Oh, well, we're always having fun. All right, we'll pick up there next time. Suppose those 3 points. And that'll give us, I won't be starting from erasing and stuff like that. Okay, homework exercises here will be any of the odds 1 through 7. Try number 9, it's a proof. Don't get bogged down with it, but try it. Do 11. Try 15, it's a proof. Again, don't get bogged down. Then do, those we've done before. Now do any of the odds 17 through 29. Those are the new ones. And any either 31 or 33 or both. And try to do 35. Okay, that's an interesting one. Okay. Then you could do either 37 or 39 or both, and we'll stop there and pick up the rest of those next time.
Dr. Fowler, when's the last day of class?
Boy. I'm guessing it's,
So what?
if
Next
the,
week. Next
it's
week.
what?
I think it's next week, isn't it?
No, okay. This is the 17th. Next Monday is the 24th. So we have class 24th and 26th. So I think the 26th is the last day of class, I believe. So,
Okay, so it's-
so we have class this week and next week.
And when is the final?
I'll give you the final on that Wednesday.
And when does that have to be turned in by?
By the end of finals week. Are you graduating? You are.
Because I just want to make sure so I can take some time off of work and get through my test.
Okay. I think finals week, I can't remember for sure. Is it Monday through Friday or is it a weird thing? Like, yeah, it may be Tuesday. If it is Tuesday through, you know, maybe we'll have one more class the next Monday. I don't remember. I don't think so.
No, I think that's the, like all tests.
Okay. So, if the next week is finals week, if you're graduating, I think since graduation is a week later, I don't think there's any problem this time. Sometimes spring terms get weird because if you're graduating, you have to have your finals early so we can get them in. But I think we have a week between finals week and graduation, so I don't think there's an issue. So anytime during finals week, if you get the final back to me during
Okay,
that.
well, I'll just take off next week and do all my tests and try to talk to him
Okay. When are you doing that?
next week.
Next week. Okay, good. I was hoping it wasn't going to be finals week.
No.
Okay, good. Okay. Yeah. Sooner the better.
Okay.
But yeah, just get them through. All right, good deal. We'll see you then on Wednesday. Well, I'll see both of you later today. Yeah. Bye.
And I was gonna ask you about Cal 3. Is there gonna be any like bonus assignment?
Well, your paper was sort of like that, and I think you're doing well, aren't you?
Yeah, it's just.
Yeah. I don't think you'll need one. I think you'll find the last test is a fairly easy one because we're having to just hit high points on 3 areas. I think those are all going to be pretty easy to do. I hope so anyway.
Yeah.
Yeah.
All right.
Yeah. All right. And I do drop your lowest test score. So that is a bonus, sort of, maybe.